As most of us already know, the best toolpath for quickly removing material or roughing out parts is a dynamic motion toolpath. Most of us will just select these toolpaths by default without giving it much thought, not knowing what's really happening that makes them, quote, better. Maybe you've looked at the resulting motion of one of these toolpaths and started to question what you're actually seeing on screen. Maybe you've noticed the changing stepovers inside of an operation. The changes that you're seeing are the result of a constant cutter engagement. And today, we're going to take a deep dive into what cutter engagement is, how it changes the toolpath stepover, and ultimately why this
It's a good thing.
So basically on the screen here, I've got a mill machine selected. I've got a really basic rectangle drawn up 6x4. And I'm going to throw a dynamic milling operation onto it. First, I'm going to do a from outside style of machining. So basically approaching this feature like it's a face of a part that we're going to machine everything off with a high-speed operation. I am going to select a 1/2-inch end mill. Just make sure I'm set to flat here. Speeds and feeds are not important. The only thing I'm really concerned about is step over. I'm going to set that at 50 thou, so 10%, and make sure this is all set at 0. I'm going to turn on arc filtering for now just because I want a little less toolpath to work with later. Okay. So it'll take a couple seconds to generate here. And there's our dynamic mill toolpath. Again, this is from outside, so it's facing away all the material. If I step into a back plot here kind of quickly, you can see it's starting from the outside and working its way in. So basically what I wanted to point out here is the difference between what can be perceived as the step over of this operation given the location of the toolpath that it's in. So this is a 1/2-inch tool. So out here we can see the distance between the two parallel tool paths here. So I'll go into analyze distance, and I'll analyze the distance between this part of the toolpath right there, and then this part of the toolpath, which should be the next cut over right there. Basically, it's close to 50 thou, slightly less, but that could just be because my snap points are a little bit off, but it gets the idea. Anyways, we're about 50 thou. So over here, you can see things look much bigger. So if I come over to this section of the toolpath and I measure from, say, that point there over to the next part of the toolpath right there. Again, I might be off by a tiny, tiny bit, but basically we're getting a step over of about 200 thou. So that's a lot bigger than the 48 or 49 thou we had over here, and it's a lot bigger than the value that we put into our toolpath of 50 thou. So what's going on? So basically, in a nutshell, I think what Mastercam has done is it's simplified this field for us. So basically what's happening in this toolpath is it's not maintaining a consistent step over. What this toolpath is in fact doing is maintaining a specific engagement angle of the cutter. So we might be able to see this a little bit better if we hop into a back plot and turn on this little quick verify button here. And this leaves a little orange trail as it goes around. And what you can kind of see, if I zoom in, is this part of the cutter here, right here, is actually doing the cutting. So that part of the cutter right there is engaged into material. So as I keep going around, basically what should be happening is this portion of the tool that's engaged, if we make that into an angle from the center of the cutter to the start of the cut, center of the cutter back to what was cut, that angle there should be consistent, relatively consistent. So when the step over started to get really big, it was closer to the inside of this part in this area here, and specifically on the ends. So even though we've got a really large step over here, about 200 thou, you can see we're still pretty consistent with that angle of the cutter that's actually engaged. Now this is not the best way to really look at this, because you're just kind of saying, well, yeah, but that's just what it looks like from this orange back plot to what's not orange. So is there a better way we can explain this and what's happening? So let's get into this a little bit deeper with what tool engagement is, how it's calculated, and how it differs. And not only when you're cutting apart from outside in, but if you're cutting apart from inside out. So maybe before we explain tool engagement angle, let's look at this exact same part. So let me just copy paste this operation. And the only thing I'm going to change is on here, I'm going to say stay inside. So the same geometry, I just want to stay inside of this square shape. And we'll have a look at the difference in the step over used between each pass on this internal feature. Okay, so there's our internal feature, obviously the part starting here. So let's look at the distance roughly between the step over used early on in the toolpath. So analyze distance, let's say between right there and about there. So 28 thou. Again, it might be a little bit off, but still that's way less than the 50 thou we've told it to step over. And let's look at something farther away from this toolpath. You know, we'll kind of look past some of the feeding motions for repositions, but over in this area, let's say about from there to about there. Again, it might be a little bit off, but now we're seeing something closer to 50 thou. So why, again, back to the same question, back in this smaller arcing area, it's way less than our specified 50 thou step over, and as we get into this larger curves, it's getting much closer. Okay, so let's have a look at what actually is tool engagement angle. So I'm going to start here. I'm going to make some extra geometry on a new level. We'll just call level 1 caps lock on, cutting geometry. And number 2, let's just call this tool angle stuff. Okay, so let's start with a wireframe. I'm using a 1/2 inch cutter, so this should make things relatively simple. I'm going to draw a 1/2 inch diameter circle. And we're going to basically try and show what's going to happen in the cut. So that's the material the cutter's left behind. We're doing a climb milling cut. Cutter rolls this way, so we're moving in this direction. And in my toolpath, I said I was doing a 50 thou step over. Okay, so basically I've got this line 50 thou higher than this line. We'll just trim this guy up so it looks better. Okay, so basically what's happening in our cut is with a 50 thou step over, this is the portion of the tool that's engaged in the cut. And we do typically talk about that as an engagement angle. So I can draw a line from the center of the cutter that contacts the actual material we're engaging. And I can draw a line from the center of the cutter to the end of the cut. So what was cut. So this angle right here is what's referred to as the angle of engagement of this cutter. Let me just make this a little bit fancier. Okay, so that's the angle we're referring to in there. So now what is the actual angle of engagement? So there's a couple of different ways we can figure this out. If you're in CAD and you don't want to do any calculations, you can just come into your drafting function here and do an angular measurement between these two lines, and you can get the angle of engagement based on this step over amount. To explain some of the math a little bit here, again, if you don't want to hear any math, fast forward a couple of minutes and skip over it. But for the most part, what's happening is we can create a right angle triangle. So again, this right here becomes our right angle triangle. And given this, we know enough information about this triangle we just drew to actually calculate this angle. We know that this side over here, let me just go into my drafting board here and make a note. This is the radius. The radius of our cutter. And this side of the triangle over here, this is going to be the radius of our cutter minus the width of our cut. See if I can reposition this a little bit better. Okay, so we said that this cut here was 50 thou. So we know that this radius here is 1/4 of an inch. This side of the triangle here, once we break this section off, is radius of the cutter minus 50 thou. So this in this situation will be 0.2. This over here is 0.25. And how do we figure out this angle given those two pieces of information? I think back to our trigonometry classes that we've all gone through. And SOHCAHTOA, if we're dealing with what would be the adjacent side to this angle and the hypotenuse, adjacent and hypotenuse is AH, which would go with cosine. So it's a cosine function. Let me just make a note here. So cosine of our unknown angle, let's say it's angle A, equals opposite, or sorry, cosine is adjacent. Adjacent is this guy over here, divided by this guy over here, our radius, which is the hypotenuse. Okay, we'll place that over there. So we know that the adjacent is our cutter diameter, or cutter radius, minus width of cut, so 0.2. Radius, 0.25. Now I'm just using my Windows calculator here. If you drag this out far enough, since our unknown angle is in this section here, we need to use the cos to the -1 function. And this calculator does work a little bit different than your normal handhelds. I have to actually do this function first and then apply the cos to that. So 0.2 divided by 0.25 equals 0.8, and then cos to -1. We're seeing theoretically this angle should be 36.87. 36.87 degrees. And to confirm it, or what you would have done in the first place, let's come in here to an angular dimension, pick these two sides, and simply snapped in the angle of that engagement, 36.87 degrees, the same that we trigged out. So with this formula here, though, this cos of the angle equals radius of the cutter minus the width divided by radius of cutter. You can start the other way around. You can be, given a known engagement angle, what is the step over that I need? So a little more in depth than needed, but let's just move some of these dimensions off to a new screen. Let's move those over to level 3 and turn those off for now. And so getting back to what we previously discussed, we've got this tool engagement angle, which I'm saying is what dynamic mill is actually controlling. And we've realized that given a 50 thou step over, our engagement angle is roughly 37 degrees, 36.87, we'll call it 37. So still, why is the step over changing throughout the tool path? So let's have a look at that. So go back to our cutting geometry, just zoom out and have a look at the tool paths again. And this is from the outside in, so like a facing motion. And it does look like the tool path is stepping over more in here. So you might assume that this tool path is in fact engaging more of the cutter given this higher step over. There's a way I can actually show the actual angle of engagement. And I think that's what I'll do right now. So I'm going to make a new level. And this is going to be cut path. Okay, so what I'm going to do is backplot this geometry here. And I'm going to save the result of this onto a new level, 255. Okay. Turn that off. Actually, I'm going to need that. Okay, so the tool paths are turned off right now. The geometry we're seeing is the actual geometry created from those tool paths. So what I'm going to do on my cut path is I'm going to take this tool path that is now geometry, and I'm going to offset it. by the radius of our cutter. Okay, and I'm going to copy this. Okay, so basically what I've got happening on the screen right now is this geometry here. I'm going to turn off the box. This geometry here is the actual periphery of our cutter as it's going through the tool motion. So as I'm simulating, you can see that the side of the cutter is going to follow that geometry. Okay, so on the other level, I have the actual path that the cutter is taking, this center of the cutter. Okay. So what I can do now is I can draw our end mill on any point along this tool cutter path. So let's just go right here. If I can find a snap point right there. And we'll draw in our 1/2 inch end mill. Okay, I'll draw another one over in here. And another one right in this section here where things start to get kind of heavy. Okay, so I'm drawing the end mill exactly on a spot in this actual tool path. Now if I switch back to the cut path, I guess I need to make these need to be on a different level so I can actually show those. Okay, I'll put those onto level 5. This is our tool. Okay, so I want to turn off the tool path so I can see the cut path and I can see my tool. I guess what I'll have to do here for this, since I placed this circle on the very first cut, I'd have to turn on the cutting geometry to set up the stock for that cut. It's not going to be accurate because typically, I've offset and it's still not at full depth over here. So this is not going to be a good example. So maybe I'm just going to omit that one for now, and I should do one maybe slightly inside. Let's go to, say, this line here. Okay, so that's going to work much better. Okay, so I've got basically my end mill has been drawn at different locations along this tool path. And I'm going to turn on the actual cut path now. So this is the profile that the outside of each cutter leaves behind. So basically what happens here was when this cutter went around and it was on this path here, it left this stock behind and it's come back around and now it's following this path. So this is the cut that it's taking right there. So I can draw a line from the middle of this cutter to the intersection of basically right there. So that's the intersection between this circle and this tool path or this cut path. And I can draw a line from the center to where it's actually engaging material, which is going to be at that intersection right there. Okay, so that's the angle of the cutter that's engaged. And if I do, let's go back to our drafting. We'll do an angular measurement between here and here. It looks like I got points instead of lines. 36.89 degrees. Okay. Let's look at this cutter here. So again, from the middle of our cutter, which is right there, to the intersection of its cut, middle of the cutter to the intersection of new stock. Again, we'll do an angular measurement between this line and that line. 37.62 degrees. So pretty close. We're an extra 1 degree of engagement. Let's look at this circle in here now, or this cut in here. So find the center of cutter there to the actual cut. Center cutter to new stock right there. We'll do a measurement on that. Angle of engagement. 38.19. Okay, so still everything's within 1.5 degrees, so very, very close. So even though the step over between the toolpaths themselves are extremely different, you know, we were 48 thou out here and we were 200 thou in here, the angle of engagement is pretty close, almost exact. So let's get into looking why that is. Let's go back to our tool engagement angle sketch. And we've got basically 3 scenarios, and I guess three scenarios is the best way to put it. One scenario is this one here. So we're cutting straight in one direction, engaging a consistent amount of geometry. Scenario number 1 would be where stock falls away from, or the cutting path falls away from the direction of cut. And the other scenario would be where stock actually falls up towards the direction of cut. So what we can do to describe these 2 situations, I'll draw a circle. Let me just make another line down here. Let's say 1 inch away. And let's make a circle that comes up to there. Okay. So with this circle, we said that this tool, we needed to do a 50 thou step over to maintain this cutter engagement. So if this is what we want to cut, this is a 2-inch diameter circle. So for a 50 thou cut depth, we need to draw a cut path that is at 2.1. 2.1 diameter circle. Okay, so notice what happens out here. The cutter is actually only engaged up to this point. So the angle of engagement here is much less. We're talking 5 degrees less. So that's why you'll see the deviation in physical step over based on how it's trying to cut material. So in order to maintain this cutting angle out here, obviously we would need to cut deeper by this amount, which we could draw a line in there. Analyze that line, and that line happens to be roughly 10 thou. So our step over is going to increase by 10 thou more. So instead of 50 thou, we need to now take a 60 thou depth of cut given this tool path. So that's an external feature. We need to actually increase our depth of cut to maintain the tool angle engagement. So let's do the opposite scenario. I think we can just mirror this guy over here. It's probably the easiest thing to do. Mirror that. And right there. Okay. So scenario number 2 is when the material or cut path actually goes up in the direction of travel. So this time we're going to make our cut geometry is going to be smaller than our tool. So we said 50 thou depth of cut. So this gives us 1.9 diameter on this type of guy. So this time, given this same 50 thou step over here, we're engaging way more than before as far as tool angle engagement goes. So now we're talking about 42 degrees of engagement instead of the desired 38. So with this internal feature, we would need to step over less than 50 thou. So maybe, well, again, we can do that exact calculation. Draw a line. analyze this line. And this line's about 15 thou long. So we would need to cut at 35 step over given this shape. So that's why you see, getting back to our original part here, the differences between this step over at the outside of the part as it comes around the outside, and things start to get drastically bigger in a physical XY step over. And with the inside part where you're seeing it starting very small, and it has a very way less amount of step over than was dictated in the toolpath. But the engagement of the cutter is what's being controlled. Not so much the step over, it's the actual portion of the tool that's engaged in the cut at any portion or any time in the toolpath. And that is what is more optimal when you start getting into these really high speeds and feeds. You need your cutter, no matter the shape that it's cutting, if it's in this corner here, if it's cutting way across a wide open area, that tool engagement needs to be consistent. So that tool engagement will equal tool pressure, deflection, tool load. All of that will remain constant given a constant amount of cutter engagement. So even though you're seeing this in your toolpath, don't think that the toolpath is doing something buggy. This is intentional. But word of caution, what can happen on parts like this, especially when you're spiraling in, when we get down near the end of this toolpath and turn this on, you can see a very skinny piece of material left over. And what can happen, especially if that material is very ductile as in it's easy to push it or deflect it or bend it, this little piece of material that's left over as you're cutting across, see if I can get a little bit closer here. What can happen is this can actually fold over. It can push away from the cut. The cutting pressure can be higher than how strong this material is to resist deformation. And if it does fold over, then your cutter could engage this whole piece that's been folded over at once. This piece could break off, and it could break your end mill. So you need to be cautious about what happens, not from the step over here, but from the actual material that's left over because of the cut. So maybe if you have something that's very, very soft and you're doing a very, very light cut over, and you might want to either increase your step over and reduce your step down so that you get a stiffer middle section here and you're cutting more at once, to prevent this piece from bending over and deflecting and taking out your end mill. So that's a word of caution about what can happen at this part of the toolpath. But yes, everything else that you're seeing happen in these toolpaths is by design, it is on purpose, and it is to maintain that tool engagement angle.